The last example we talked about on Monday was basically is an array sorted. Okay, let's review what the problem is. You're given an array, and for every recursive call, we do not want to create any brand new array for the performance reason. Okay, we talked about that last time. So now, what we're going to do is we're going to pass an array and also a range of indices from and to. And then that's effectively going to tell us which part of the array we're going to look at. And let's say this, let's do this simple example here and then do another harder one. Okay. Now, that's about the some examples over here, but we'll do some new example today as well. Let's have a look at the code very quickly, and then we'll trace it all together. Okay. Now, this is how the code looks like for isSorted. Okay. Now, you can see that we are defining two methods over here. Okay. Let's have a look at them. The first method we're defining is called isSorted. That's basically the method you will call at the top level. That one there simply just take a single array as arguments. And then in turn, this method here is going to call another helper method here, which is called isSorted helper, right? That there takes not only just an array, but also it's going to take a range of indices, right? It's going to say for this particular array, let's start by looking between element at position 0 and element at the last index over here. And now let's have a look at what this method would, how this method can be defined. It has a special name called recursive helper method. So the recursion actually happened in this particular helper method here. So we got an array as input, and also we say from where to where. Initially, it's simply from the first index to the last index. Okay, so far so good? Now, the idea is typically you have two base cases. When you have from is larger than 2, typically you should have from less than or equal to 2. But if you get the negation, that simply means an empty range that we're considering. It's as if we are considering an empty array. In this case, empty array is automatically sorted, so return true. Okay? And the second base case is if the from and to indices are the same. That means there's only a single element in the range that we're considering. So it's as if we're considering a single, like an array of size 1. Okay? In that case, array of size 1 is automatically sorted as well. So we also return true. Okay, so far so good for the two base cases, right? I would say most of the time, if you're trying to follow this particular pattern over here, you should always start with these two base cases, right? Either empty range or a range of size 1. Okay, these two are the base cases. Now, what about the else part? The else part basically says that, well, if the array is more than I can handle in the base cases, the length should be at least 2. What I should do is, I'm going to say the elements at from and the element at from plus 1, which means from and the next element, right? So these two should be sorted, less than or equal to. And then, recursively, I want to make sure the rest of the array is also sorted. I'm combining these two results using conjunction, right? The %. So I'm calling this helper method over here, but now notice what's going to happen. Whenever you're calling recursion, make sure you're dealing with a strictly smaller problem. How do we ensure that? Well, we pass the same array, call by value, and we say that now the starting index for us to consider will be from plus 1. That means the range of element to look at will be strictly smaller, right? Just one element smaller, okay? We did the example for it's all positive last time, so now this is just another instance of this, okay? Any question about the code structure over here? You can see the code structure here, I would say 80% of this code over here is the same as the code for is all positive that we talked about on Monday. Basically the same. The only difference really is over here, how you deal with the test base case number 1, how you deal with base case number 2, and also how you actually combine the recursive call and then also some other value together, right? That's kind of what you have to be creative about for every new problem. Okay? And you do something similar for your lab number 7 as well. Okay? Question about the code before we do some tracing. Okay? Everybody so comfortable with this? Okay, good. Let's try to trace it all together. Basically, what you have to be very careful about is how the from and to are going to change. Specifically, from plus 1. Let's see exactly how it is going to happen. Okay? What I would do is, I already got a tree over here, so it's easier for us to trace. What I would do is, let's consider two arrays. Array number 1, A1, is simply 3, 6, 6, 7. It's sorted, so that should be returning true. The second array that we'll talk about is simply not sorted. Okay, let's consider two arrays and see how the recursion goes. One is going to return true, the second one is going to return false. But let's see exactly how that's going to occur. Before we get to the specific examples about A1 and A2, because for both of them, the size of the array is simply just 4. So which means we're looking from index 0 to index 3, and also from index 0 to index 3. Right? That's how we start by calling the recursive helper method. Okay, let's see how we do that. Okay? Both of the programs have the same recursion tree. Okay? So you start by calling isSorted and pass the array over here, which can be A1 or A2. And then which will in turn call the recursive helper method here, right? It's going to be isSorted helper. I will simply say is sh, okay, isSorted helper. And then we pass the same array, which can be either A1 or A2. And starting from 0 until we reach 3, okay? And then let's focus on the big picture before we go to the specific example. For every recursion call, so this will be the first recursion call. This will be the second one. This will be the third one. Let's see how the from index is going to change, right? For the very first recursion call, remember we used to have the, let me use a color to highlight. You can see over here, we started with to say, starting from index 0, we want to go all the way until the end, right? Now, the first recursion call is going to say, now let's narrow down the range a little bit to have a strictly smaller problem, in which case we simply got 1 over here, right? You can see we go from 0 to 1. And then the next recursion call, it will be from 1 to 2. And then the next one from 3 to 3. And now, when you get to this particular recursion call here, let's see here, isSorted helper 3 and 3. You can see that's one of the base cases, right? So 3 and 3 is exactly this particular base case, which means there's only one element in the range to look at. And that will be the point to actually return. Okay? And for each recursion call, we also have to make sure we compare the elements at that particular recursion. For example, when the from is actually 0, we compare 0 and 1. When the from is actually 1, we compare 1 and 2. When the from is 2, we compare 2 and 3. Right? That's kind of the big picture for both cases. Any question about the general tree structure over here before we go on to trace each one of them? Okay, I hope that's clear. All you have to really pay attention to is how the from index over here really changes its value in each recursion call. Okay, that's really critical. Otherwise, you got infinite recursion. Okay, what I would do is I'm going to wipe out whatever I just said over here, and then let's trace it and see what's going to happen. Let's do the first one. The first one, we are expecting the result to be true. Okay, let me also get rid of this, get rid of that. Okay, it's completely clean. Okay, let's say we want to do, let's use blue over here. Let's say we want to trace for A1. Okay, that means A over here is going to be replaced by A1. Let's trace A1. Okay. Also to remind you about, let me just put A1 here. So A1 is basically pointing to this particular array, and then we got 3, 6, 6, 7. Okay? To really distinguish between indices versus elements, indices would be 0, 1, 2, and 3. Okay? So now let's see what's going on here. Okay? Now, when we try to do isSorted over here, we're going to call the recursive helper method isSorted helper, right? What we will do is we're going to call this particular one, so we go down at isSorted helper. The same array, in which case it will just be A1. Okay? And then we say that the starting index is 0 always. And the ending index should be A1.length minus 1. Right? That's why we got 0 and 3. Okay? What this means is, let's see this. So that means when you got 0 and 3, that means we want to consider the entire array to begin with. Okay? So how do we consider this particular array? We're going to break it down into 2 tasks. What we will do is, first of all, we want to make sure for this particular one, these first 2 elements are basically sorted. That's why you see A0 less than or equal to A1, right? And then the rest of the array is also sorted. How do we know the result of the rest of the array? You should look at the recursive call. So what you will have is another one. Let me just use a different color here. So what you will have, for example, orange, you can see we got this recursive call with 1 and 3. So what does that mean? When you got 1 and 3, that means not only that not only that, these two elements are sorted, which is considered over here. But also, we want to make sure the rest of the array, starting from 1, ending at 3, is also sorted, right? That's what that recursion is going to handle. Okay? It's going to return either true or false. Okay? So now, before I go on to the orange part, let's just try to figure out the result over here. When I got A0 over here, A0 is 3, and A1, sorry, A0 here is 3, and A1 here is 6, right? That is sorted. So that means I simply just get true for this part. But I don't know what the recursion result is just yet. I only know for sure this particular pair of the elements. But for the orange part, I need to figure out from the recursion. Okay? Now, let's go on with the orange part. Let's go to this particular recursive call. So what we have is, first of all, for the orange part, let me use orange over here. We want to make sure the first two elements for the orange part should be sorted, right? In that case, A1 and A2. A1 over here is 6. A2 over here is also 6. 6 less than or equal to 6 will give us true, right? However, we still have to worry about the rest of the array. For the rest of the array, the way we do it, let me again use a different highlighter here. Let's say pink. So that means we have to make another recursive call. In this case, starting from 2 until the last elements. So that means we are really considering this part of the array. You can see we keep narrowing down the range of indices that we are considering for the array. So how do we deal with this further case? If we are considering this pink part over here, what we should do is, first of all, we have to make sure these two elements for the pink part, A2 and A3, these should be sorted, right? So what's A2? A2 over here is simply 6, and A7 over here is, A2 is 6, and A3 is 7, right? Over here. So that one there, 6 less than or equal to 7, is going to give you true. Right. Now, how do we make a recursive call in this case? That means we have to now worry about how to deal with the rest of the array. Let me use one more color here. Let's say simply blue. What we want to do is, we want to do 3 and 3. 3 and 3 simply means we are dealing with basically this particular range over here. And now you can see the range has only one element to look at, as we learned before in the base case. If you look at the base case here, 3 and 3 is simply just this particular base case over here. And that should return just true. Okay? In that case, we know that, let me just try to write it down. That means for this part over here, this is the base case. Okay? Where from is equal to 2. That will simply just give me true. That's the point to return. So once I got return true from over here, I can combine true and true over here, right? Every level, we simply got conjunction over here. I forgot to write it, okay? Because you can see that the way we combine the recursive result is by using conjunction. So all of them should be combined using conjunction. So once I get return true over here, true and true will give me over here true, okay? And then I got true here. I got true for this particular recursive call. So true and true will give me over here also true, right? And one more thing to say, and then this will be true and true over here. That will also give me true. So eventually, I just get true, which means this particular array is sorted. Questions?
I found it enough to compare 3 and 3.
Well, 3 and 3 over there is simply just a base case, right? When you got 3 and 3, that simply means you only got one element to look at.
I understand that part, but I'm saying how did it do that way? But I'm saying before we compared like from and to.
Uh-huh.
Right, like 2 and
Well,
3,
if you look at the code over here, you can see that when from is equal to 2, we don't actually do something like this, right? It's a different branch. Yeah, when they are equal to each other, that means we are considering only one single element. One single element is automatically sorted. That's why we just get true. That's how we reach the base case.
I know that it's equal to true. I know why it's equal to true, but I'm saying masking. Oops, that's the
Okay, that's fine. Guys, any question about this? Guys, don't be shy. It's the second last class. I want to make sure you're comfortable with the exam and also 2011. So do speak out. Yes?
This is more of a question expected to like handle cases where like from is greater than
2,
even though
it's actually,
even though we wouldn't call it that way?
oh, you might call it that way. It's a good question. So Jordan's question was, how can that first if actually happen, right? Basically, you're asking that. Okay, it's possible. Let me just say that. How can this branch be executed? Here's how. It definitely can happen. What about I simply got something like this? Let me write some Java code here. I say integer, let's say a1 is simply just empty, right? And then I'll simply say print, for example, and then I can say is sorted over here, and then I say a1.
Okay, usually I just like deal with those.
That's okay. Yeah, but you're right. But how you exactly write a code, that can be, we can discuss after class, but I'm saying this is a more general pattern, which means always talk about empty array, an array of one elements, and also larger array.
What I mean just is like, do our recursive methods have to not like generate an error even if they're used like in cases we wouldn't?
Because since in the problem description itself, if you look at the problem description here, right? Since we simply say over here, determine if an array of integer are sorted or not. We didn't say empty array will be considered as an error. So somehow you have to deal with it. Yeah, either you deal with, as long as it's dealt with. Yeah, of course. When the TA or myself mark your exam paper, we'll see. But I would say it's definitely one way to solve it. But in the exam, yes, you will be expected to write something like that. But by the way, guys, make sure you show up in the class on Monday. I'll talk about the exam. Not recorded. Okay? Hopefully that motivates you to come. But you come anyway, so it doesn't matter. All right. Any? Yeah.
Empty case is always true.
Not necessarily. So I'm saying that you definitely, for every recursive problem on the array, you should definitely think about what's going to happen to the empty array as a base case. But how exactly you deal with the empty array is up to what problem you're solving, right?
Can you go back to the last one? Yeah, so my question was, no, the previous one, where you traced it. Yeah, my question was, how did it know not to do 3, 4? I know 4 isn't there, but how did it know not to do 3, 4?
Because, so your question is, why would it not say 3, 4 over here rather than 3, 4, say 3, 3?
I know that's right. How did it know?
The reason is that how you define a code, right? Over here, you see that every time we make a recursive call over here, we simply keep 2 the same.
Okay.
And then we say from plus 1. That is why, let's say, when I want to go from here to make another recursive call, this 3 here will just remain to be the 3 over here. On the other hand, 2 will be incremented to 3 over here. Right? That's how the recursive method is defined. Yeah. Of course, it would definitely be an error if you simply say 2 plus 1 over here. Right? That's basically what you're asking. If you define your code wrongly, of course, it's going to behave wrongly at the runtime. Good. Guys, are we okay with this example here? Any other questions? Yes, go ahead. So you're asking another recursive problem, right? You say we want to solve recursively the minimum value from the array. Yeah. Okay. So I'll talk about it conceptually, and then it can be left as an exercise for you. Okay? That's good. I like the question. It's also possible. Let's say this. We are still talking about an array. Okay, like this. Let's say, for example, I'll give you. Let's say we got 3, 2, 1, 6, and 7. Okay? We know that the minimum value is simply just 1 at index 2. Okay? Now, how can we know pretty well how to solve this problem iteratively using a loop to find out the minimum. How can we solve this recursively? The same pattern. The same pattern. Which means somehow you have to consider the first element first, and then maybe I can recursively get something from the rest of the array, and then do something with these 2 values together and get a final result. The orange is basically something you can do right away. The green is something you can assume is going to work. How can you combine the orange and green all together so that they work together to get you the minimum for the entire array? Anybody want to try? Okay, Yeah, go ahead.
It's just like the one we just get 3 and compare it to the one just beside it, see if it's larger, we just...
If you only, okay, good. If you're saying that you only compare 3 with its neighbor, right? That's not really recursion, but let's say you compare 3 and 2. Okay, sure. And you know that 2 is smaller. And then, what do? Where is the recursion going to occur? Okay? How about this? I'll give you a little bit hints, okay? Okay, the hints is hopefully this will help a lot. Again, every time you're trying to solve the recursion, don't be shy to actually make some assumption. You definitely can make assumption. Assumption in the sense that when you try to make a recursive call on a strictly smaller problem, you can assume the solution return for that strictly smaller problem is going to be correct. Okay? What I mean is, let's say this. I'm given an array where the indices are from 0 to 0, 1, 2, 3, 4. Okay? The problem I'm trying to solve is it's going to be from 0 to 4. That's the indices, right? Now, what if I can tell you that I can definitely tell you what the minimum is from indices 1 to 4, which is the green part. I can just tell you. You don't have to compute it yourself. I can just tell you. If I can tell you what the minimum is in the green part, how can you use it together with the orange part and figure out what the minimum value is for the entire array? What do? Just compare them. Exactly. That means, well, let me sketch the code. If A is empty, okay, no minimum, let's say. Else if A is size 1, and then you can simply return A0. Okay, so these are the 2 base cases, right? What about the else part? Else part simply means I want to somehow compare A0 and the rest of the array. Okay, so what I can do, I can say integer, I'll just say min. Min of the rest is simply equal to, let's say I'm defining a method called min, okay, which will take A and also 0 as a starting point, and also A dot length minus 1, okay? And now the minimum of the rest will simply be, I make a recursive call to say min, the same array, but now I simply say starting from 1, or I can say from plus 1, like how we did it before, right? From plus 1, and then I will say 2, okay? That's how I get the rest of the array, the minimum. And then I can simply now say if A0, which is the orange part over here, is strictly smaller than the minimum of the rest. So what does that mean? That means which one is the minimum? A0. So I can return A0. Otherwise, I know it's the other way, so I can say else return the minimum of the rest. You can see, again, the pattern is pretty much similar to what you would do, but you follow the same pattern. But just the recursive part and the specific handling of the base cases will be different. Okay? Okay, any question about this? That's also something reasonable to expect. Okay? You can definitely try on Eclipse and see if that works. Okay? All right, any questions about this? Yeah?
What the number was saying?
Okay, sure. If both numbers, well, that's a little bit back to 1022, right? If both numbers are the same, so it doesn't matter which one you return, correct? Yeah. In that case, we just go to else part. Yeah, because strictly small doesn't satisfy. Okay, so I did prepare another example here for isSorted over here, which you should expect to return false, but it will be left as an exercise for you. Follow the same tree and then try to see why this particular one is going to return false to you rather than true. Okay, the same procedure. I'll leave that to you. Okay? Guys, any questions before we go on for another harder example, another one? Yes?
How do we handle the previous slide case where you have like a list like 0, an array like 0?
You're talking about this particular case or?
Finding the minimum that will return in that case, or even an empty array.
Oh, empty array, good question. So you can see that I'm just trying to lay this out over here to say if A is empty, I'll just say no minimum. It's kind of informal. You can either throw an exception, or you can print out an error, or you can do something. Yeah, so I kind of leave that to you. Basically, what you have to consider is you got to do something when the array is empty. But how you deal with it is up to you. Okay, good. All right, so now let's now go on to another topic over here. I do have another topic over here. I'd like to discuss maybe after the binary search. So something about correctness proof. Let's do this a little bit later. Okay, I will just get back there in just a moment. Let's now do a binary search. Okay, it's a very interesting problem you're going to solve. Basically, let's motivate you for this particular problem here. Why do we need binary search? And there's a very important assumption about how you can, under what circumstances can you do binary search. Let's go from the beginning. When we talk about hashing before, let's say I'm simply giving to you, let's say 0, 1, all the way to, let's say 10 to the power of, oh, you don't see that, right? Let's say that's an array over here, 10 to the power of, let's say 6. So we got 1,000,000 elements, let's say 1,000,001 elements in the array. That's why we got so many elements. So now, let's say you're given this array here, and every element in the array is simply just an integer. Let's say maybe 3, maybe 2, and then not sorted. And then 26, doesn't matter. Okay, we got 1,000,001 integers over there. Now, if I want to implement a search to say, does the number 23 exist in this particular array? Okay? That's the problem we are trying to solve. I want to search a particular element to see if that exists in the array. Okay? The best we could do, based on what we have learned, is to use a loop. Right? If you simply use a loop, you can simply say, well, I can say for, right? The best I can do is to say for integer I is 0. Let's say this is a. And then we can say I less than a.length. And then I plus plus, right? And then I would say if, let's say a at position I is exactly equal to the element, let's say the element I'm looking for is x, let's say x. Well, actually in this case 23. Is exactly equal to 23, and that means I can return true. Okay? Otherwise, I return false eventually. Oh, sorry. Otherwise, after the loop, I can say return false. Okay, let's say that. Of course, it doesn't have to be 1,000,000. It can be of size n in general. Now, this seems to be the best we could do, right? Because you can assume nothing about the structure of the array. The elements of the array can just be randomly distributed, right? Just random. Okay. What would be the worst case in terms of big O? Yes.
23 was like at the end of the year.
Yeah, that would be the worst case, right? So what would that be? In general, let's say, n, right? Because in general, if the array size is n, then the worst case will be is simply at the end of the array. So you got to do all the, you got to traverse all the way to the end. So in general, it's simply bigger of n. That means if it's 1,000,000, you may have to go for 1,000,000 iterations, right? If there's a trillion, you go for 1,000,000,000,000 iterations. Okay, let's clarify that. Make sure we understand this. Now, what if I tell you the following assumption you can make? Let's say the array is already sorted. If I tell you that, if the array is already sorted, let's say in the increasing order, okay? Let's just assume all the elements inside the array is just unique. There's no duplicate. Let's assume. Now, let me just go for another page over here. So now, there is a very important assumption over here. Let's say assume the input array is sorted, okay? Which means if I'm giving this particular array over here, let's say I got maybe minus 23, and then 2, and then 2, and then 3, all the way to something, right? And then eventually maybe I get to 1,000, right? Again, I got 10 to the 6 minus 1, the index, okay? From 0 to there. I got the same size of the array. So now, of course, we can still use the original loop over here, in which case it will still be big over n. But if we can be given this particular assumption, we can do better. Okay? We can do better. So now, there is a method called binary search. The reason that it's called binary search is whenever you're trying to search something in the array, you can choose either branch. When I say either branch, I will try to explain that a little bit further. Okay? Basically, the search space doesn't have to be the entire array. It can be just half of the array. So what do I mean? For example, let me be a little bit more concrete over here. Let me just say we have another array, let's say just of size 10. Let me just say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, we got from index 0 to index 9. Okay, so that's the array we have. Okay, it's sorted. Now, I want to know whether or not, let's say 9 is there. I want to know. It's pretty much close to the end. If you simply do the linear search, it will just go all the way to the end of the array. But now, if we know that the array is sorted, what about we try the following? What I would do is, rather than starting from the beginning, I want to start from the middle. Okay, the middle. Okay, in this case, the middle is basically over here. This is the middle, right? Pretty much, that's the middle. If I just go to the middle over there, you can see that 5 is not equal to 9. But now I'm reaching a difficulty here. So now, should I go to the left or to the right? How do you know? This is really important to understand binary search. How do you know if so you're claiming that I can just go to the right, right? How do you know if I go to the right, I wouldn't miss the element if that's what's in the left? How do you know? Okay, if it is sorted, what does that mean? If it is sorted, that means every element to the left of this particular middle element here must be less than or equal to that. Agree? Because we know the element we are trying to search is already larger than this. So logically speaking, it's not possible to be on the left half anymore. Okay, so we start from the middle of the sorted array, and then we want to see which direction we should go. Of course, if the middle element is already the element we are searching for, we are done. If it is not there, we want to know whether we should go to left or right, either way, not both. That's why it's called binary search. You go either way, either left or right. Okay, let's say after the first, of course, we will see how we can define this binary search recursively, okay? Once you understand the conceptual idea. So that means we know that 5 over here is strictly less than 9, so that means we have to go to the right half, okay? So that means after the very first decision, we can already narrow down the search space by half, right? It's divided by half. Now, for the green subarray over here, what we want to do is we choose the middle. Let's say pink. Let's say somehow the middle is over here. Let's say we choose the middle. Okay, now we compare the middle over here and the element we're looking for, right? In this case, where should we go? To the right or to the left? To the right, right? Because you can see that the element we're looking for is 9, which is strictly larger than 8. So now we know that we should go either left or right. But in this case, we should go to the left, right? Because it's guaranteed every element in this particular half is going to be smaller than or equal to. So there's no way it is there. Okay? So now we go to the right. So what we'll do is we'll go to the right. So that means we'll go to the right. Okay? So now the pink array over here is, again, we have to decide. Let's pick the middle elements. And in this case, maybe we're lucky, we just pick the middle element being 9. In this case, 9 is the elements that we're looking for. And then we're done. I'm just being a little bit informal here to give you some intuition. In the case of the linear search, you always start from the beginning. In the case of the binary search, you always start from the middle. In the case of linear search, you make a progress in the loop by simply move on to the right neighbor. In the case of binary search, you make a progress by truncating the wrong half and go to the right half, the correct half, depending on exactly how the middle element is compared to the target element that we're looking for. That's binary search. Any question about the conceptual idea over here before I move on to the code? Okay, basically when you see the code in Java, it's not very long, but the critical part you should really pay attention to is how do we calculate the middle elements over here, right? How do we know where the middle is? How do you figure out the middle index? If I know the starting index is 0, the ending index is 9, I can simply add them up together divided by 2. That's how I get the middle index, right? Once I get the middle index, I can know what the middle element is, and then compare that with this one here, right? And now, if I know this, I should go to the right half, that means I should really somehow update the range of indices to look at. In this case, it would be exactly from here to here, right? This would be the new half to look at. And this is where the recursion occurs. Okay? That's only conceptual. Okay? Let's have a look at how the code will look like, and we'll try to trace it together. Okay? Questions about the idea? Okay? Let's see how we can do that. Okay? So that's a binary search code. Okay? Maybe I can try to use some animation over here. That might be a little bit slower. Okay, you can also look at the description over here. But let's just look at the code. How do we do binary search? So, but for the binary search, you're going to take 2 inputs. You're going to take a sorted array. The array must be sorted. Okay? If the array is not sorted, then you simply cannot go this way, right? Because if you go to the left, you might miss something on the right. Okay? Okay, we got a sorted array, and then we got some key or element you want to search for. Just call it key. Okay? And now, what we will do is we'll do another helper method like what we did before. We'll simply say we're going to have the sorted array called by value, starting from index 0, ending with the end of the array, the entire array basically. And then we're looking for this particular key. So that's the recursive helper method we have to define. Okay? Now, let's see how we can define this particular recursive helper method. So we start with sorted over here. Okay? And then we have from and we have to, and then we have the key. Okay? Now, let's see what the base cases are. So base cases will be easier to handle. So from is larger than 2. As we said before, if from is strictly larger than 2, that means we're considering an empty range, like an empty array. Can an element exist in the empty array? No. So that's why we return false. Okay? I'll show you an example to see how we can reach there. But that's one base case. But what about if there's only, let's say from is equal to 2? Then what should we do? If from is equal to 2, that means we're only considering one single element. But how do we know we have found it? Well, you check to see if that particular element is the same as the one you're looking for, right? So if from is equal to 2, and then remember from is the index. So we'll say sorted array at position from is equal to the key. If it is the case, then return true. If it is not the case, return false. Okay, so those are the 2 base cases. So what's okay? Okay, now let me give you a little context, and then we'll figure out exactly how to make the recursion. Okay, now first of all, let's see how we can calculate the middle index. The middle index is simply from plus 2 divided by 2. I will illustrate this on the iPad. Okay. Okay, let's have a look. This is how you can understand the method here. So binary search helper. Okay. So what we have is we have an array A, we have from, we have to, and also we have also the key that we're looking for, right? So these are the 4 inputs to the recursive helper methods. Conceptually, let's say this. If we have an array that looks like this, okay? And then let's say the from index is simply just here. That's a from index, okay? And this is the to index, okay? Now, how do we figure out index for the middle elements? Well, in this case, you can see that from the calculation there, we simply say middle is equal to from plus 2 divided by 2, get a quotient, right? Okay? So now this is the middle, okay? And middle is very easy to calculate. You simply say from plus 2 divided by 2, okay? Okay? Now we got the middle over here, and now what should we do? What we should do is we want to figure out exactly what this element is. Easy, just go to. So this is the array called sorted. It's called sorted. Just be consistent with the slides. It's called sorted. So this is the array. So now what we should do is we want to see if sorted, let's do the case analysis over here. If the key that we are looking for is less than, strictly less than, let's say, strictly less, let's say the array has no duplicates. It's less than the sorted array at index middle. Okay, now, what I should do is I should really try to make a recursion on some half, right? Either the left half or the right half. First of all, should be either left or right? Left, right? Good. Yeah, you are left over there. Yes, we should go this way here, right? Oh, sorry. There's a less sign over here, so that should go to the left half. So now, how exactly do we make the recursive call? That's something I want to show you visually so you understand when you see the code. So what I would do is I would say binary search helper over here, and then I can tell you that the first one is going to be sorted as well. Okay, so now we need to pass something here, and then the key we're looking for remain the same. And as you agree, we should really say the new place we want to search for should be, since we know the middle one is, the middle element is already larger than the key. That means we should go to the left. Conceptually, we should really go to this particular half, right? Excluding the middle elements, because that one has been dealt with already. So now, how do we update the range of indices? If you see from the diagram, how should we pass? What about the first index? Should it still be from or from plus 1 or something? Well, you can see that over here, right? Over here, you can see the orange part over here. The orange part is from to here, right? So that means I should put from over here. What about the ending index? Used to be 2, right? Used to be here. But I can narrow down the search space by half. What should I put over here? Should I put middle or middle minus 1? Middle minus 1. If you put middle here, it's no point because middle has been dealt with already. You don't have to worry about it anymore. So middle minus 1. Okay, that's how one of the recursive call. Let's say we go to the other case. Let's say else if, okay, I would say if the key that we're looking for is strictly larger than the sorted array at position middle. Let's say. So now we're going to make another recursive call. So you can say conditional, right? Either this or that. So now binary search helper over here, again, call by value, I'm going to have sorted here, one thing here, and then the same key. And now, to make distinguish that, we know that in this case, we're going to go to the right half, right? Conceptually. Now, what should I put for the two numbers? Middle plus 1, okay, I agree. What about the second one? 2. Okay, that's how the logic works. That's exactly what you will see in the code. Again, you can see it's more or less following the pattern we just taught you in the previous examples. Number 1, you have to think about the base cases. When the array is empty, or when the array has only size 1. Okay? And number 2, when you talk about the recursive cases, you have to somehow update the from and to indices. In this case, we update both. Possible, right? And we update them conditionally. So this will be a very nice case study for you to see how the pattern can be applied. Okay, so now let's go on to the final code and see how it looks like. If you go to the final code over here, that's exactly what I just talked about. Okay, let me just mention that here. So you got a middle index calculation over here, and also we got something called middle value, which is at the middle index. And then we say if the key is strictly smaller, we go to the left half, in which case it will be from to middle minus 1. If key is strictly larger, we go to the right half, in which case we say middle plus 1 and then 2, right? Like that. Guys, any question about the code? The most important thing for you to understand is how we came up with this particular mechanism, right? Especially when you say from middle minus 1 versus middle plus 1 and 2, and the relations over here, right? That's really important. A very nice exercise for you would be, you can see over here, the sorted array that we assume is in ascending order, right? It's increasing. Here's an exercise for you. I would suggest you do it, okay? I'll write it down. The exercise for you is modify the binary search. Modify the binary search so that the input array is also sorted, of course, but in descending order. Okay? That's the change. Okay? How would you modify that? Conceptually, how would you do it? What should you change, really? The code. What should you change? Well, basically, you got to do something over here, I can tell you. Okay? Think about it. That will be an exercise for you. Okay. Now, that's about the binary search. I want to do just one more tracing with you, okay? I did prepare 2 examples for you. I'll do one together with you, but the other one, exercise. Okay? Let's do one. Now, without referring to the code, basically, I'm going to show you exactly how the middle index will be calculated, how we update the from and to. Let's do it together, okay? Let's say we have an array over here, A, and then we got the size will be 9 elements, okay? So here indices from 0 to 8, okay? And it's sorted in ascending order, okay? Let's say we want to do a binary search. I just call it search. Binary search, we pass the reference of A, and then we want to search for the elements 18, okay? 18 does exist in index 5. You can see it, right? Let's see exactly how binary search can be executed. So as soon as we call binary search with these 2 arguments, what we should do is we should really call the search helper. This should be search helper, okay? I meant to say search helper, okay? The search helper over here. You can see the binary search helper, okay? Let's just see that. Basically, we pass the same array A, the same array A, and same array A, right? So now what you should really watch for would be, and also the same element 18 is being sought over here, okay? What we should really notice is the changes on the from and to. That's the critical part, okay? Now, let's look at this particular one, okay? The first one. Let me use a different color, okay? This one here, okay? First of all, let's calculate the middle index. What's the middle? Let's see this. Let me just make sure I'm consistent. Okay, middle versus middle value, okay? I'll just say that. Middle index would be, in this case, 0 plus 8 divided by 2, 4. That means I'm looking at this particular value over here, right? And then we got middle value in this case is 15, right? So 15. And now we know that the value we are looking for, 18. We know that 18 that we're looking for is strictly larger than 15, right? That means we should go to the right or the left? The right, right? Because the one we're looking for is 18, which is strictly larger, right? So how do we go to the right? Well, if you want to go to the right, you have to execute this part of the code to go to the right. But let's see exactly how we do it, okay? So now, if you want to go to the right, conceptually, you're basically doing the following. Let me just use some highlighter here. You basically want to go for this particular half, the right, okay? In that case, what you will do is, you can see that at the moment, what you will do is, the middle is basically 4. So we want to do middle plus 1. So 4 plus 1, that's how you get 5, right? This is the middle plus 1. So 4 plus 1, you get 5. And then the 2 value over here remain to be 8. Okay, that's how you got 5 and 8. That means we're now looking at a different range on the right half, which is the blue one over here. Okay? Okay with this? Okay, let's go on a little bit. So now, let's have a look at this one here, which is green. So now we're looking at this particular range over here. Let's say we are looking at between 5 and 8. So now what's the middle index? So the middle in this case will be 5 plus 8 divided by 2, which is 6 quotients, right? So that means we're really looking at this particular element over here, right? So that's a new middle. And also we got the middle value being 21. Okay, 21 here. All right. And then after that, we want to compare this middle value with our key. In this case, our key is 18. 18 is strictly less than the middle value 21. In this case, should we go left or right? Left. Good. Very good. Now let's see how we can go to the left. Let me use orange over here. So that means we should go to the left. That means something like this. Basically only here, right? It's going to be middle minus 1 and then the front, right? Okay, good. Let's see how we do that. I'll just show you how the calculation goes. Okay, you can see it's going to be middle minus 1. So middle is exactly, let me say this. This guy over here is exactly the middle minus 1. The middle is exactly the 6, right? And the front part remain the same. So that's how you got the 5 and 5. So now, for this particular call over here, are we reaching a base case over here? We are, right? Because if you look at what we are highlighting over here, the range is as if we're considering an array of size 1. Okay, so now, what should we do? Well, we simply compare to see if this particular element over here is in the base case. Let me show you the base case. If you look at the base case, when from is exactly equal to 2, then we simply compare to see if the element is the one we're looking for, right? In this case, what we will do is we simply say sorted, okay, this is from, okay, this is from, at position 5 equals 18. In this case, yes, so that will be true. That's how we return true. Okay? Every time you make a recursive call of the binary search helper, you truncate the wrong half, go to the correct half. Either go to left or go to right. Are we okay with this? Binary search? It's not difficult. Let me just say one more thing before I take a question. So how can binary search be useful? The very important assumption is the array is sorted. It's a very important assumption. But how can you be sure the array is sorted in the first place? You may have to do the sorting yourself. And I will definitely at least cover merge sort, as I keep promising, in our last class. I'll make sure I do that. But you are going to learn about other different sorting algorithms. Oh. Is it test? Oh, they're testing. Okay. Yeah. Okay. All right, we are fine. Otherwise, we got to evacuate. All right. Okay, anyway, how is this relevant to your 2011? In 2011, binary search would not be the focus. The focus will be how can you establish the assumption for the binary search? How can you sort an array? But I will at least cover one for you. That's efficiency. Okay? Now, okay, any question about binary search? Okay, so in order for you to actually trace it, I'll leave this as another exercise for you. Okay, just this one here. Okay, how to trace it for the binary search. Oh, okay, sure, good, no problem, no worries. Yeah, okay. Yeah, we're safe. Don't worry. Yeah. All right. Exercise for you. Try to trace this particular one for the binary search, but I already got hints for you over here. You can follow through. Okay, I suggest you do the exercise. At least you can understand better how the binary search work and how the two indices actually work. Okay. Now, next topic. Now, what I want to do is I will leave the running time and correctness maybe in the beginning of Monday. Okay. What I want to do is another interesting problem. It's called the Tower of Hanoi. Okay. Not too sure how many of you have heard of it. It's actually a very interesting problem because, let me just look at the problem altogether. And then we'll see the recursion, and then I will show you the code. Okay, running time we'll talk about next time. Oops. Guys, you know what? It's very bad because I lose the picture for Tower of Hanoi over here. You know what? Give me just one moment. I definitely want to show you the picture of the problem. It's really important. Any one of you heard of Tower of Hanoi before?
Yeah, we have to do it.
Oh, 1019. Okay, pretty much know what it is, right? But you know, I should be fair. For those of you who haven't heard of it, we should see that. Okay, I will show it to you. I just want to show you one picture. Okay, if you look at the recursion lecture notes over there, at least you can see the picture there. Okay, that's a picture I want to show you. Okay, that's basically you got 3 packs, and then you got 8 disks. I think that's the original game. I believe there was a myth. I forgot the detail. Somewhere on the planet, there are several monks actually doing this kind of puzzle. They got lots of disks on the pack, and then the myth was, as soon as they're done, it's going to be the end of the world. But mathematically speaking, it's going to take them more than 10,000 years to do it, so we are fine. Okay. Yeah, I'm not sure if that's true or not, but I will try to look up the story. I forgot. I didn't have time to look it up. I'll look it up and show you on Monday. Anyway, that's Tower of Hanoi. But to be fair, let's see how the game can be played, and then let's play it together. The very interesting bit about this example here is, when you look at the problem itself, you cannot imagine you can solve it using an array. You just cannot imagine, but you can actually do it. Okay? Now, let's make sure we're on the same page. If you look at that, we got a tower of several disks, but for our purpose, we only consider 3 disks, okay, as an example. And also got 3 packs, and now the rule is very simple. You can always only move 1 disk at a time. When you stack up the disk, only the smaller one can be on top of the bigger one. Okay, so these are the 2 rules. And now, what you want to do is, maybe I want to transfer all the 8 disks over here to another pack. Basically, that's what I want to do. Okay, but let's do example together. Okay. Now, Tower of Hanoi. Oh, actually, I do have the picture. I forgot. Yeah. Let's say we got 3 disks. Okay. Let's play it together to get intuition. Again, once you get intuition, I only have to explain to you a little bit more details about how the code looks like, and then we are done. Okay. Let's now play the game all together. We should have some time. We should have more than 20 minutes. Now, what I would do is, I will leave this handy over here so I can keep copy and pasting. Copy? Good. Let's start with the game in this way here. Let's say initial stage. Let's have some coloring convention over here. Let's say we have a big one over here. This is 1 disk. Let's say this is C. Okay? And then we have a middle one. This one here, oh, we can see that, right? Just want to make sure. And we had a smaller one in the middle, that is B, okay? And then we got another one, green. That is smallest is A. So that's the initial setup for the game, okay? C, on top of, you got B, and on top you got A, CBA, okay? Because A is the smallest disk. So now, here is the puzzle, okay? We want to somehow move the stack from P1 eventually to P3. Okay? Now, how can we do it? For those of you who know the rules, how should we play? For example, let's say, what about the second one? Do we have any choice for the first move? Not really, right? Because the only one you can move is the top one. Okay? So now, should I move A to P2 or P3? Well, let's say, okay, eventually I want to move from P1 to P3. Let's keep that in mind, eventually, okay? And if, hypothetically, if I simply move A just to P3 already, would that work? No. Okay. We'll see. You can try, but I can tell you that it's not going to work. Okay? What we should do is, what would be your suggestion? A to P2? Okay, let's try. Okay, basically what I would do is I'll move A, the smallest one, to P2, let's say. And then I will actually, so that means the remaining one is something like this. So C here, and also I got B here. Like that? Okay, now what would be the step? Anyone? Yeah, go ahead. What should I do? B to P3? Nope, that's not going to work. The thing, if you put B into P3, that means you can, the only one you can do, it would be from, for A from P to P3. Then you're doing the wrong direction.
Okay, so from B to P2, and then...
But you cannot put B into P2 because B is larger than A, right? That's good. We are confirming the rules. Well, what about moving A from P2 to P3? Okay. Yeah, what we can do is, what about we simply do this? Let's say for here, C here, and then we have B here, and then we simply put A here. Okay? Now, next. What about the next? Well, we can move from B to P2, right? You know what? Definitely I'm going to run out of space. So what I would do is, I'm going to make this smaller.
Wait, so then why did he, if you're just going to go to the third step, why don't you just do it right away? Yeah.
Okay, so this will be smaller. Let's do it again. Okay, so what we should do is, let's try this. So now we should really move from B from P1 to P2, right? Let's try that.
Exactly, why not just get rid of the second step altogether?
The second step, what do you mean?
Because you just put A to P3 anyway.
Oh, am I doing that? Oh, yeah, why do I need that?
Yeah.
Oh, yeah. I'm not sure why I put it that. Okay, good. Sorry about that. Let me get rid of this. Sorry for the confusion. I really didn't mean to do this one here. A should be in P3. So what I would do is I'll get rid of this. You know what? I'm gonna draw more efficiently. I'm gonna forget about the being beautiful, the picture. Okay? Let me just draw manually. Okay. I should need more practice. Over here, okay, let's say this. Okay, let's put A here. Okay, and then move on to the next one. Yes, so over here, C here, and we got a B here, right? Okay, as before, so now, why don't we move the B here? And then, so only C here, right? And then A here. So far, so good? So now, next one, move A on top, all right? Okay, the reason I'm doing the whole move is I'm going to illustrate to you something to do with the recursion. Okay, and then we got C here, doesn't move, and we got B here, and then we stack A on top. Okay, up to now. Okay, good. I will put a star over here. It's more like an intermediate point. Oh, thank you. Yeah, don't worry about it. Okay, good. Let's go on with this. Okay, let's now go on to the next one. Let me just erase these guys over here. Okay, so now what will be the next step? Eventually, we want everything to be moved to P3, right? The rightmost one. So now let's move C to the rightmost one. So now what I would do is, I would do like this. What I would do is I'll move the C here to here. Okay, so B and A are still here. No, you can only move one disk at a time. All right? Okay, we're almost done. Okay, let me just move them a little bit here. So now we're almost there. Okay, so now, finally, so now, what will be the next one? We cannot put A directly on C, right? Because that means B has nowhere to go. So what we should do is, one way to do it would be, we can maybe simply put, let's say this. Let's say C is over here. The idea is we should somehow move A away, maybe. Okay, and we have B here. Right? And then we can move B and then A. Okay? So we got two more steps. Okay, we got C here. And then we got B here. And then finally, we can put it. C over here, B over here, and we got A over here, right? Okay, that's basically the move. Okay, now, anyway, next year I should really put the picture over here so it's easier. All right, so now how can we understand this solution here? It's only 3 disks that we are doing over here, okay? But now, what if I say we got 8 disks? How can you figure out a solution by yourself? Okay. Now, before I move on to show you the iteration over here, I already got the source code available for you. So let's have a look to see how to run this source code. And then I go back to the iPad illustration. So if you look at the source code over there, we actually got a method called Tower of Hanoi. Okay, we'll look at the detail for the code in just a moment. Okay. So what I want to do is, I just want to show you to get some intuition. Basically, I will simply pass the disk. Let's say I only got a single disk, for example. If I got a single disk, the program will simply say, move disk A from pack 1 to pack 3, right? Move the disk from pack 1 to pack 3 directly if there's only one disk. Okay? Now, what about we got two disks? If we got two, let's say over here, let's see what the program would say. It's basically saying you want to move pack 1, move A from 1 to 2, and then B from 1 to 3, and A from 2 to 3. Okay, you can execute the program and make sure that's right. Okay, if we go back to the original problem that we are solving on the iPad over here, this is the A, B, and C. Right? If you look at that, basically this is something they would say this many moves. Okay, somehow they correspond to what we just illustrated over here. Okay, but now apparently this is only conceptual. But how can we turn that into this program over here? Okay, that's the issue we got to deal with. Okay, I'll get there. And you can also try for fun. If let's say you got actually rather than 3 disks, you can also do 4. Okay, they can also do it for you. Okay, that's the steps you need. Basically, it's more like a game solver. It can tell you, given this many disks, it can tell you exactly the move you have to take. You can even try 10. Okay, you can try that by yourself. Okay, let me go back to the version where we only got 3 disks. And then let's get some intuition over here. Okay, so this is the complete solution for when you got 3 disks. So I'm going to leave the connection to the diagram over here to you, but let me just go directly to the Eclipse input, the output over here. Okay, so now if you look at that, I want you to look at just this part over here. If you only look at the one I'm highlighting, okay? So what is that part, really? If you look at that, let me just, I'm highlighting something on the iPad, and then I'll show you. So what are the first 3 steps are really doing? What are they really doing here? Somehow we're not really moving C, right? We're basically saying that like this. Yeah, exactly. In order for me to eventually move in order for me to eventually move these 3 disks from P1 to P3, I can divide that into 2 parts. First of all, why don't I simply take the top 2, which is A and B, and somehow eventually move them, since I know the target is simply P3, so I will call P2 the intermediate one. Eventually, I want to move A and B, the top 2, into the intermediate one. That's really the first stage is doing. Okay, can you see that? Let me say it again. If I got 3 disks over here, I know that eventually I want to move all the 3 into pack 3, right? We can divide that into 3 phases. First, phase number 1, we can say the top 2 over here, we want to move them to some intermediate pack. And that's exactly what we're doing here eventually. But to really complete this particular phase, we need some multiple moves. Okay? And then this particular middle step, if you look at the Eclipse over here, how does it look like? That is simply just to move C from 1 to the target. That is exactly over here, from here to here. Right? That's the third step. And now, conceptually, what we are really doing over here, let me just use another one here. Let's do the pink. The final 3 is the third phase, basically. What does the third phase do? Questions or? Oh, you guys? Wow, you should have reminded me, right? All right. Guys, why are you so shy, in the second last class? Okay. Anyway, okay, we got 3 phases over here, right? The first phase is orange. The orange part corresponds to the first 3 moves over here. Okay? That simply move A, B, the top 2, from the first from the P1 eventually to the intermediate one, P2. Okay, that's the first one. And then the second phase, we simply move the largest one over here from P1 into P3. Okay, what about the final stage? Somehow we want to move these two who are currently in the intermediate pack, move from there to the top over here. Okay, that's what the pink stage will do. So the pink stage simply just corresponds to the last three moves over here. Okay, question about this. Okay, so now, how do we solve this recursively? How do we solve that? Okay, basically, I already mentioned how you can solve that recursively. Let's see the description of the solution. Okay, let's see that. So now, in order to solve this recursively, there are three steps. Okay, step number one. In general, let me see this. Okay, in general, you may have n disks over here. You may have n. N can be 1, can be 2, can be 8, can be 100. Doesn't matter. So now, in general, there are three phases. So phase number one, you want to move the top n minus 1, except for the largest one. You want to move them rather than from P1 to P3, but from P1 to the intermediate one, which is P2, right? That's exactly what this is doing, from the P1 into P2. Okay, that's the first phase. And then you want to move the largest one, which used to be at the bottom, from P1 to P3, the targets, right? So that means this phase over here, from P1 into P3. Okay? And then the third phase is basically to say, whatever you have moved to the intermediate one, move them back to the target, P3. So now, where do the recursion occur? Which step are the recursion? If you think about recursion, recursion means we are really talking about a strictly smaller problem that we're trying to solve. The original problem is trying to move n disks from P1 to P3. And in phase number one, we are trying to move n minus 1 disks, which is strictly less, in that case, into the intermediate pack. So that's like a subproblem, right? And then the third stage is also another subproblem we are trying to solve, which is also recursion. In that case, we're moving from P2 to P3. Okay? So these are the two places where we got recursion. So now, this is the solution pattern, but now how do we solve that recursively, right? Now that's the issue we have to deal with. Okay? Let's have a look at the code quickly, and then I'll trace it next time. Okay? Let's just try to understand the code structure over here. Okay? Again, the most important thing for you to understand, if I want to move from P1 to P3, I need to make sure somehow the top disks, except for the last one, except for the largest one, are moved to the intermediate pack. And then they are eventually moved back. Okay? So these are the steps. But how do we do that? Okay, let's see. Okay. Let's look at the code. The code overall is like this. So we define a method called Tower of Hanoi. Okay, we simply take a string array over here, and it will just be disks. We're assuming that the first element in the disk will be the smallest one. It's going to be sorted in the ascending order, right? In this case, it can be A, B, and C. A less than B less than C. Okay? And then we simply call the recursive helper method TOH, Tower of Hanoi, helper. We give the same disk by call by value, and then we pass the entire range of the disks. So 0 until disk.length minus 1. And now we say that we want to move from pack 1 to pack 3. Okay? Basically like this. We want to move from P1 to P3. And now, how do we define that particular helper method there? Okay, let's have a quick look. So we got Tower of Hanoi, helper over here. We got the disks, we got from, we got to, we got P1, and we got P2. Okay? So now, now we got to talk about the base cases, right? So now we got these two base cases. I will deal with this a little bit later. Okay? Now let's look at the recursive case. That's exactly the three phases that we talk about. So when you study this example here, what you should really review are these three phases conceptually. But let's see how these three phases are reflected in the code. Okay, let's see phase number one. Phase number one over here and phase number 3 over here. Both phases involve a recursive call. Okay, now the same disks called by value. And then also, let me just try to highlight to you the one you should really look at. Okay, the same disks over here. And then let's have a look at what intermediate really mean. Okay, intermediate over here. I want to show you this first. Intermediate. Intermediate simply means, I'm just doing a little bit trick over here. If I know I want to move from 1 to 3, so what should be the intermediate? This here simply the arithmetic. I know that I got either a 1 or 2 or 3. The summation is simply 6. If I know that I want to move from 1 to 3, the intermediate one should be 2, right? How do I calculate that? I simply use 6 minus 3 minus 1. So that's how I get the 2. Okay? That's how you will see that. Okay? So I'll simply say whatever the intermediate one it is, I'm going to say 6 minus P1 minus P2. That's how I calculate the intermediate one. Okay? Now, what's really tricky is the following. Okay? How do we understand the way we pass the parameters over here? Okay? From 2 minus 1, and let's understand this. From and 2 minus 1. How do we understand that? If you look at the argument over here, we're saying that we're going to move these many disks from and to. Originally, it's simply from 0 until the largest index for the array, right? That means all the disks. So now what we want to say is we only want to move maybe only A and B, the top two. So the way to say that would be starting from the same from index, but for the 2 index, we want to exclude C. How do we exclude it? Well, you just say 2 minus 1. Okay? That's why you got a 2 minus 1 over here. And then, how do we specify the direction of moving? Okay? I want to say, when I say 1 and 3 over here, I basically, 1 and 3 over here, you're basically saying move from P1 to P3. Right? That's basically what the method means. But now, how do I say I want to move from P1 to the intermediates? You simply say P1 over here, and then intermediate. So this means move from P1 to the intermediates. In this case, intermediate would just be P2. So that's exactly the first phase. I want to basically move from P1 to P2. And the top 2 disks, which is A and B, right? So eventually what I will get is exactly this result. Okay? That's how the method is defined. And now, in the third phase, well, I'm just going to move them back. So you will see exactly a from and 2 minus 1 over here, but you can see the 2 variables are swapped. So now I want to move from intermediate back to P2. Okay? Now, I will trace the code on Monday. Okay? Now, finally, this is the second stage. Now, let me just say this, yeah, and then I'll take your question. The second stage is we're going to move the largest one to the remaining free pack, right? How do we do that? The way to do that is we're going to say what the top packs will just be from to 2 minus 1. So the one that remains will be just at index 2. Okay, I'll say from this at position 2 and from this P1 to P2. Okay? Questions? The last phase, you mean the... You mean, okay, which line are you talking about? Are you talking about this line here? The last one, yes. Intermediate to P2, yes, it should be P2. Intermediate would be, it's whatever value it is by doing this particular calculation, 6 minus P1 minus P2. That's what you want. Yeah, you want to make sure you first calculate the intermediate over here. As we'll see in the recursive call, we don't have time today, but as we'll see in the tracing next time, the intermediate value depends on what P1 and P2 is. Okay? Okay. I'll stop here, and then make sure you come to the class next time. We'll start with some more examples, and then we'll talk about the exam.